Okay, welcome back. This is chapter 19, and it's entitled Aldehydes and Ketones and Nucleophilic Addition Reactions. Okay, so we're going to continue forward with some of the most important concepts in organic chemistry, and that is nomenclature of aldehydes and ketones, but also reactions that they tend to undergo. And you've had a little bit of this already when we talked about the Grignard reaction, also the sodium borohydride reduction of aldehydes and ketones, as well as the lithium aluminum hydride reduction of esters, so on and so forth. So this won't be brand new to you, but for the most part it will be something that really enhances our knowledge regarding carbonyl chemistry. So, as an introduction, I have a generic representations of both an aldehyde and a ketone here. If we were to draw the structure of an aldehyde, this is what they look like. Recall that aldehydes have a carbonyl flanked by at least one hydrogen. And what you see here on the right, this is an abbreviation of an aldehyde. Okay? In other words, here's our bond to, say, an aromatic ring or something like that, followed by the letter H, followed by the letter O. Now that's very important. Okay, you wouldn't want to write COH. Okay, that would be different. That's more like an alcohol. So when you see the letters CHO, bear in mind that represents an aldehyde. So what would be the simplest aldehyde possible? The simplest aldehyde possible would be one where we have hydrogens on both sides of the carbonyl. And you probably have heard of this aldehyde. It's called formaldehyde. Okay? This is the structure of formaldehyde. It's the simplest aldehyde there is. And if we were to write the abbreviated structure, it would be like this: HCHO. Okay? This is formaldehyde. Most of the aldehydes, though, will have an R group there. Now let's go to the other side where I have the generic structure of a ketone. Ketones, of course, are different than aldehydes in that they have carbons on both sides of the carbonyl. Okay, and again, we can abbreviate it using this string of letters. And sometimes, if you see it abbreviated, you may see brackets around this CO, like that. And just be mindful, if you see it that way, the CO inside the brackets, that's the carbonyl. Alright, that's the carbonyl functionality. And these R groups can be the same, or they can be different. They can be alkyl groups, they can be aromatic rings, so on and so forth. So the simplest of all the ketones that we have would be this one. Okay, let me just draw the condensed structure of that for you. And this one you should also recognize. We use this one oftentimes in the lab to clean our glassware. And this has the common name of acetone. Acetone. Excuse me. But if you were to name it systematically, okay, we put these carbons in a row, 1, 2, 3, like that. You could call it 2-propanone, right? 2-propanone. And for reasons you'll see later, the 2 here would be redundant. You don't need to do that. If we wanted to abbreviate acetone using that process there, we could simply sketch a methyl group with the carbonyl inside and another methyl group on the right. Pretty rare that we would do that. Anyway, that's sort of an introduction to aldehydes and ketones. Let's flip over to page 120 and let's go through the nomenclature of aldehydes and ketones. Now, like I've always told you, if you were good at naming alkanes, then you're going to be good at naming just about any compound in organic chemistry. Let's begin though with aldehydes. Let's start with aldehyde nomenclature. Now the suffix is very important. The suffix is going to be AL, right? The letters AL. That's what you're going to see at the name, at the end of the name of an aldehyde. Remember you had OL for alcohols, you're going to have AL for aldehydes. And furthermore, just like with alkanes, the longest chain has to have the aldehydic group. So these are things that you've seen before. We're not reinventing the wheel here. We're not looking at anything really brand new. We're just kind of applying some previous knowledge. All right, so let's give this a try. Let's look at sample problem 19.01. The first thing you need to do is recognize, okay, that you need to find that longest carbon chain, just like you do with any other organic compound. But by default, this is carbon 1. Okay, always begin with carbonyl. Then this becomes carbon 2. Now we know we need to go this way so we get our longest chain versus going that way, which would be a shorter chain. So these are carbons 3, 4, and 5 respectively. Now what does this tell us? This is going to give us, okay, the parent name of the compound. Once you find that longest chain, we have our parent name. And what would that parent name be? Well, because it's 5 carbons, it's pentanal. Pentanal. Okay, so we're applying the rules that we see here at bullet point 1 and bullet point 2. But you know it's not pentanal per se because we have some branching groups. Notice we have a group branching off of carbon 2. We have a group branching off of carbon 4. And just like in times past, you would have to name those branching groups. This is the 2 carbon unit on carbon 2 that we come to know as ethyl. Okay? And at carbon 4, this is simply a methyl group. Okay, so we need 4-methyl to indicate that branching group. Now these are all the elements of the name, this being the parent and these are branching groups. And recall that you have to place these in alphabetical order in front of the parent. So E precedes M in the alphabet. So the final name here would be what? It's 2-ethyl dash 4-methyl and pentanal. So use this example as a model of a branched aldehyde, keeping in mind that by default for chains the carbonyl is going to be carbon 1 for aldehydes. Now the second example here is a little different. Okay, you know this is a cyclohexane derivative. Well, it turns out if you have this group branching off of a ring of any size, it has its own name. This, as we've come to know, that's an aldehyde. CHO is an aldehyde. And this has its own name, just like a methyl would be CH3, a chlorine would be Cl, a bromine would be Br. This is called carbaldehyde. It has its own name, carbaldehyde. Okay? And what's the carbaldehyde attached to? It's attached to a 6-membered ring that you know is being cyclohexane. So the name here is simply cyclohexane carbaldehyde, all one big word. Okay. Cyclohexane carbaldehyde. All right, plain enough. Now there are some common aldehydes that we encounter in organic chemistry. One of them I've already alluded to earlier. And there's a few of these I would like you to commit to memory. All right. Well, let's just take a look at these with their formulas in one column and the common name and systematic name in the right-hand column. Okay, this again, the simplest aldehyde is this one. Common name is formaldehyde, and the systematic name, because it has one carbon, would be methanal. Here's another one. This is the next highest homolog. This is acetaldehyde. It has two carbons. Its common name would be ethanal. Then we have propionaldehyde, propanal. We have butyraldehyde, butanal. This is valeraldehyde, pentanal. So you probably recognize the systematic names in terms of how it correlates to the structure more readily. All right. But there are a few of these I would like you to commit to memory. Okay. But let's just kind of go over this one more time. Remember what the letters pH meant? Right, that's phenyl. So you could actually call this benzene carbaldehyde. But the more common name is benzaldehyde. So this is the one that I want you to commit to memory. Right? Please memorize this one. If you do, it's going to be very useful because we're going to see benzaldehyde over and again in a bunch of reactions. Okay, so case in point. If we were looking at benzaldehyde, okay, and again, I want you to know its formula. I want you to know its common name. And don't be too concerned about the systematic name. But what is this telling us? What does that structure look like? Well, we have one of two ways that we could draw it. One way to draw it would simply be to recognize that it has a benzene ring. And furthermore, we would recognize that it has an aldehydic group attached to it. So we can use the letter CHO. Most of the time, though, we're going to draw it like this, using the line bond illustration, because we're going to be discussing reactions, and it's just better to do it that way. So please memorize that one, okay? It's very useful to know, because we're going to be seeing it on a regular basis. Okay, that pretty much does it for aldehydes. Let's move down to ketones, okay? Go through some ketone nomenclature. Now, ketone nomenclature is a little bit different because you know that here we're going to have carbons flanking the carbonyl. But the biggest difference is that the suffix, okay, is going to have ONE in it. Okay, it's not pronounced one, instead it's pronounced own, okay, for ketone. Now, here's the distinction between this and aldehyde. The longest chain must contain the carbonyl group. So the carbonyl group will not be carbon 1 like it is in aldehydes. Okay? So let's give these a try. I have a chain and I have a ring here for you to practice. Okay, so this is the branched chain ketone, and we're going to provide a systematic name for it. Okay? Let's give that a try. Now, as you know, you have to number from one end to the other. And the reason we're going to start on the right-hand end is because that's going to give us a lowered numerical designation for the carbonyl. So if I start numbering from the right-hand side, this is going to be carbon 1, 2, 3. But if I started numbering from the left-hand side, it would be carbon 1, 2, 3, 4, 5. Always number from the end that gives you the lowest numerical designation. So I'm going to go ahead and put that 3 in there as a reminder, because we're going to need that in the name. So let's supply the other numbers. This is carbon 1. Carbon 2, we already said that was 3. Here's 4, 5, 6, and that could be 7, or this could be 7. Okay? Now, the reason we do that now is because this is going to allow us to come up with the parent name. And the parent, of course, is going to have HEP in it, but we're going to go ahead and indicate where that carbonyl is in the parent. So the parent's name manifestly is going to be 3-heptanone. 3-hep for 7 carbons. We put the A there for phonetic reasons. 3-heptanone. And keeping with what we've learned in times past, we have to name the branching groups. We have a group branching here at carbon 4, which is nothing more than a methyl group. We have a group branching at carbon 6, which also is a methyl group. How often have we seen that? So you know that we have 2 methyls, that's called dimethyl, and what carbons are they bonded to respectively? carbons 4 and 6. So it's 4,6-dimethyl needs to go into the name. Alright, so here we have the prefix, here we have the parent. So let me provide you with a systematic name of this. You already know what it is, but I want to show you a subtle variation for one of the names. Most of you would just call this 4,6-dimethyl -3-heptanone, okay, which is fine. However, you have the option of placing the 3, which is the position of the carbonyl, over here between the N and the O. Okay? And fact is, you would drop that N. So let's do that. So here's an alternative name. And this is a little more modern, but feel free to use whichever approach you prefer. 4,6-dimethyl -3-hepta. Now -3-one. This is kind of like naming alkenes and so on and so forth, where in alkynes where you could place that number in front of the actual functionality. But either one of these is fine. Either one's fine. Let's do the second example on the bottom of page 120. As you can see, we have a 6-member ring here. Okay, let me go ahead and write the number 6 in. And here, we're going to name it as a ketone derivative. Now, I bring that up because that's going to mean that this is carbon 1 by default. Okay? And you know that you have to number in a direction that gives you the lowest possible number for the branching group. So we're going to go clockwise and stop there. So the parent name here for this compound is what? Cyclo, because it's a ring. Hex, because it has 6 carbons. Unknown. Alright, this is the cyclohexanone derivative. And you recognize the branching group at carbon 2, at least you should. So therefore the systematic name for this cyclic ketone would be 2-isobutyl cyclohexanone. Okay, you can barely see my O there. That's 2-isobutyl cyclohexanone. And of course, you could also call this a 2-methylpropyl group if you preferred. Irrespective of that, this is a perfectly acceptable systematic name for a ketone. All right. Now I'm going to flip over to page 121 of the lecture notes and talk about some common ketones. And they're the ones that I might want you to commit to memory. And it's kind of unfortunate that we didn't make our way back into the laboratory, because we were going to actually use some of these. And but oh well, that's the way it is. So here I have a list of common ketones, kind of like I have with common aldehydes back on an earlier page. In the left-hand column I have their formulas, okay, written out. In the middle name I have their middle column I have their common name, and the right hand there's a systematic name. Okay, there's a few of these I want you to memorize. Okay, let me just put the word memo next to it. All right, I want you to memorize this one. Okay, and this is the simplest ketone there is. But I'd also like you to memorize this one, because we're going to see this one in a lot of chemical reactions. Okay, so again, what do they look like? This is again is acetone. Which has this structure when we write it condensed. And there we go, like that. And this one's called acetophenone. Okay, acetophenone. Acetophenone would be the simplest ketone that have an aromatic ring. This would be acetophenone. Okay. All right. So commit those ones to memory. What I mean by that, I want you to know their formula. I want you to know their common name. And you don't have to worry too much about the systematic name, but you could do that anyway. So on and so forth. Here we have the formula and the common name. Pretty rare that we call this 1-phenylethanone, okay? But that would be its systematic name. See if you can make sense of these systematic names. Okay, a good practice for you might be to say, for example, cover all these up, okay, and then draw those ones out on them that you see under systematic name. Now, with propanone, some people place a 2 here in front of the P, but it's redundant because by default the carbon has to be at position 2. So really when you have 4 or more carbons in a ketone, then you have to tell the position of the carbonyl. Okay. All right. Now here's some acyl groups. These are the, okay. You don't have to memorize them, but they're really handy to know in the context of a discussion. So generically speaking, okay, this is called an acyl group, right? Called an acyl group. You may remember the Friedel-Crafts acylation, and we installed an acyl group when we did that. Here's a specific acyl group called an acetyl group, okay? And this one actually is part of aspirin. Okay, that's why aspirin is called acetyl, which means acetyl salicylic acid. So acetyl groups themselves have only just a methyl group bonded to a carbonyl. See that? That's an acetyl group. And the aldehydic group can be referred to as a formal group. And similarly, if you have this group here with an aromatic ring, it's called a benzoyl group. Okay, so these are some common acyl groups that we're going to encounter, particularly when we discuss chemical reactions. All right, now speaking of chemical reactions, here we go. Much of this chapter, at least the first half, is a review of what you've had in previous chapters, particularly back in chapter 17. But let's talk about them again. Okay, preparing aldehydes and ketones. You remember the Dez-Martin periodinane? Okay, it was a very complex species that had a high prevalent iodine atom in it. And I said all you really needed to know was that if you see the term Dez-Martin periodinane, you just needed to know what it would do. And, well, what does it do? Well, we have to look at, in this case we have an alcohol, but what kind of alcohol? This is a primary alcohol, right? And what happens when you oxidize a primary alcohol? You get an aldehyde. So this is a way, a very good way to make an aldehyde. So we went from 1, 2, 3, 4 butanol to butanal. Okay? So the Dez-Martin periodinane expressly is for doing this type of conversion. Okay. And similarly, if you have a secondary alcohol, such as this one, this is 2-pentanol, what happens? You oxidize it to a ketone. These are very good chemical reactions. So here we go from 2-pentanol to 2-pentanone. All right, this is an oxidation because you're increasing the electron density between the oxygen and the carbon. That's why it's called an oxidation. Okay, so if you need a review of that, just go back to your chapter 17 notes and or chapter 17 of McMurray, or if you want to look on it on OWL, you can be my guest. Now there is one reaction that McMurray had in times past that he no longer lists, okay, but we still see it from time to time. And in effect it does the same thing that the Dez-Martin does, and that is the use of PCC. Okay? So notice here we have PCC. Okay? Now PCC is an acronym for pyridinium chlorochromate. Now this has lost favor over time, but it's still used. But one reason it's used, it lost favor, is because it has chromium. Okay, and the chromium in here is very toxic, so we tend to get away from that. But you might notice that the results is the same as the Dez-Martin. So here, what do we have? We have a primary alcohol, benzyl alcohol, We oxidize it with PCC and dichloromethane to benzaldehyde. Okay? So just be aware of this, okay? If you see the letters PCC followed by dichloromethane, okay, you get the same results as you had when you did Martin. Now, continuing in this vein of how to make ketones and aldehydes, let's go back again a little further to our favorite chapter. This is chapter 8. Okay, chapter 8. Remember ozonolysis? Remember ozonolysis? Ozonolysis, okay, was a way to cleave pi bonds. And more specifically, you could cleave a carbon-carbon double bond or even a carbon-carbon triple bond. But in this case, we're going to cleave a carbon-carbon double bond. All right. So just as a reminder, what are we looking at here? Remember what O3 was? This is ozone. Okay, this is ozone. Ozone is a very, very powerful oxidant. So step 1 is called ozonolysis. And then step 2, okay, we use zinc and acid as a reductive workup, okay, to quench this reaction. So how does this work? Well, the simplest way to do this, okay, is just find your carbon-carbon double bond and recognize that it's going to be cleaving between, okay, between this sp2 carbon and that sp2 carbon. Now, in terms of figuring out the structure, it's real simple. All one has to do is draw that entire ring system minus, okay, minus the entire double bond. Leave everything like it was. And then at the spot of cleavage, okay, go ahead and place carbonyls, right? So if you do that, okay, you end up with the product. So you might notice that this and this are the same. It's just like drew this out in a zigzag fashion. The important thing to recognize is that nothing changes in this molecule. This methyl group is still there. Okay, this hydrogen, it's still there. And you can count the number of methylenes in between. 1, 2, 3, 4. 1, 2, 3, 4. So ozonolysis in this case gave us what? On this end we have a ketone, and on this end we have an aldehyde. Alright? And that was owing to the uniqueness of the starting compound. Okay. This next example is brand new to you. You said, no, we had reduction of esters back in chapter 17. But you didn't have it, okay, using this particular reagent. So let's take a look at this one. This is new. Right? This is the new reaction for you. You haven't seen it before. But I want you to take notice of what you see on the reaction arrow. First off, it's a two-step process. Okay? The first step is using an organometallic compound called dibol. And it also uses the solvent. This is toluene. You think about it. And this is a very low temperature. Okay? The low temperature is very important for reasons I'll point out in just a second. Alright, now you're wondering, how do you get minus 78? Folks, minus 78 is when you have dry ice, in other words, solid CO2, and then you mix it in with acetone. Okay? And what it does, it makes this really, really cold slurry, but it's still liquid. And it plummets that temperature down to minus 78. And step 2 here is just to quench the reaction. Okay, so let me just write in acid quench as a reminder of what's going on here. If you were in the lab, you'd simply add acid until the pH was 7 or below, somewhere along the line. So let's talk about this reduction. What are we beginning with here? On the left-hand side, we have an ester. Okay, esters are characterized by carbonyls with an sp3 oxygen here and another carbon there. Okay, so the ester features of this molecule are right there. Okay, those 4 atoms constitute the ester. The carbonyl, that oxygen, this carbon. You can have just about anything else you want connected to those four atoms and still have an ester. But what's the result? The result is an aldehyde. And in this case, this would be what? Propionaldehyde or propanal. And finally, over here on the right-hand side, you might notice that we have methanol. And methanol is simply the cleavage product of the ester. So this is a ester with a methyl group. Now, let's talk a little more closely about how this is going on. First off, DIBA is an acronym. Notice it's all capital letters for diisobutyl aluminum hydride. Okay? And here I have it in condensed form. Now, if you're interested in what that structure looks like, you could draw it out. Okay? What we have here in effect is an aluminum atom with a hydrogen. Okay? And we have two isobutyl groups. So I'm going to go ahead and sketch those in. Okay, so that would be the structure of diisobutyl aluminum hydride. Now, one cool thing about this, and this is why it works, that aluminum is sp2. Okay? And that means it has a vacant p orbital, and therefore it's going to be a very powerful Lewis acid. Now, what does DIBA really function as? It serves as a hydride source, which makes it what? A reducing agent. It's a reducing agent. Okay? And as I mentioned moments ago, a very low temperature is necessary. Okay? And you say, why? Why do we need to have it so low? Well, it's not just because it's so reactive, okay? But the very low temperature is necessary to avoid over-reduction. To avoid over-reduction. Okay? So what is over-reduction? If you have this at room temperature, this aldehyde, the carbonyl, would get reduced all the way to the alcohol. It would keep going until it was the alcohol. But if you want to stop it at the aldehydic stage, okay, you better conduct the reaction at low temperature. Now, in the next row, what I'm showing you here is how this system actually functions. Okay, let's talk about that for a little bit. What I have here is a representation of the DIBA, okay, where I've used the letter R for the isobutyl group. You're going to form a complex by this sp2 oxygen, okay, acting as a nucleophile towards the aluminum. Okay, in other words, these two are going to come together to form what we call a diba-ester complex. Okay, a diba-ester complex. So these two came together to do that. Now, at this point, we have an intramolecular transfer of hydride. Okay, meaning that this hydride is going to go right there. Okay, it's going to transfer immediately over into the adjacent carbonyl carbon to reduce that carbon, and one of the pair electrons, the pi bond specifically, will break to form a tetrahedral intermediate. And then there's a few subsequent steps that we go on, and we form our aldehyde. Okay, so take a look at McMurray for a little more details regarding that. But just remember, what's the purpose of a diba reduction is to convert an ester into an aldehyde. Okay, so we're now at a point where we can actually review what we've just gone over. So let's go ahead and fill these in. And the thing about this particular series of reactions is that they're all designed, okay, to give us the same product. In this case, we're looking for a way to make pentanal. One way to do that is by using ozonolysis. Okay. Here we have hexene. Notice a 6-carbon unit, but if we want to cleave right there, how will we do that? One way is to use ozone, okay, and that would be by using the ozone generator. But you have to quench it And to quench, we'd use zinc, okay, and some acid. Now, this is what McMurray has, but really what most people do in step 2, and this is what I always did, was to use something called dimethyl sulfide. Okay? Dimethyl sulfide has this formula. It's simply 2 methyls bonded to a sulfur, and it has abbreviation DMS. Okay? It's really better than zinc and acid, but either way you get the same results. So that would result in the formation of pentanal as a major organic component. Now over here on the right, how can you go from pentanol to pentanal? We've learned that there's 2 ways to do that. One of those ways is the Des-Martin. Okay, let's write that in. Des-Martin. And it's called a periodinane. Periodinane. Okay, Des-Martin periodinane. Which is really a very good way to do that, but this reagent's super expensive. Okay? The cheaper way, but very effective, is simply to use PCC, which I referred to earlier as pyridinium chlorochromate. And technically, if you do PCC oxidation, you really need a chlorinated solvent. Okay, it doesn't work very well with ordinary solvents. But either of these approaches would result in the oxidation of a primary alcohol to an aldehyde. And then finally, we're going to convert this ester. This is called methylpentanoate. Okay, methylpentanoate, which is again an example of an ester. You write that in. One way you can spot an ester, the most important way, of course, is to look at the structure. But if you see the suffix -08, okay, that kind of tells you that it's an ester. Well, this is the one that we're talking about on this page, okay? The first thing you would want to do is simply add DIBA. And notice it's all capital letters. This is what McMurray uses, DIBA. Others have an L there, they call it dibol. But he called it DIBA, so we'll live with that. And you'd want to have a solvent, and we choose toluene because toluene, first of all, will dissolve this ester, and furthermore, it doesn't solidify at this low temperature. Now, this is critical. You must write this in, guys. Okay? I need to see that. If you don't write that in, okay, if you just have this and this, then this ester is going to become, okay, it's going to become one pentanol. It's going to go all the way to there, okay, because it's such a powerful reducing agent, you end up over-reducing it. And then finally, in step 2, you want to quench it by dropping the pH, and we do that by adding acid. So this is a Bronsted acid, H3O+, or you can just write the word acid. Right. But these are the sets of reagents and conditions that are necessary to convert any one of these different functionalities into a common compound, in this case, pentanal. So you want to remember these. All right. You've had this one before. You had this one before. Sort of had this one before, but this one here is brand new. Okay. This one's brand new. Okay, let's keep going a little bit further. Let's go to page 123 of our lecture notes. And let's just see how we can prepare ketones a little more. None of these are going to be surprising to you. Remember moments ago that I mentioned that you could oxidize primary alcohols to aldehydes? Well, guess what? You can oxidize secondary alcohols, in this case cyclohexanol, to ketones. What's an alternative approach here? What could you have done just the same to get the same results? That's correct. You can use the Des-Martin. Okay. So another approach to doing the same reaction, okay, is just to use Des-Martin. Now I'm not going to write in periodinane. You already know what I'm talking about, the Des-Martin. And secondly, we just said that here's another one from chapter 8, which is ozonolysis. How do we do that? Look for the carbon-carbon double bond, break it here and here, place carbonyls, okay, at each of those positions. and then suddenly you've got your compound. And also remember here you could also have DMS. Okay, DMS is dimethyl sulfide. Okay, sometimes you see that with the letters DMS. Either way, okay, those are effective measures for quenching the intermediate to the final ketones. And here's another one you had back in chapter 16. I think all of y'all did really well in that chapter. This is using the Friedel-Crafts. In this case, Friedel-Crafts acylation. What's going on there? You're going to replace what? One hydrogen with whatever group you see here. But let's just remind ourselves what these things are. What is that called? Well, you know now that this is an acetyl group, right? So this would be acetyl chloride, which is an example of an acid chloride. And of course we have our catalytic aluminum trichloride here. And you end up doing a electrophilic aromatic substitution. So we replace that hydrogen, okay, with this entire acetyl group. So what do we end up with? This is the one of those that I wanted you to commit to memory. This is acetophenone. So what's a good way to make acetophenone? Benzene plus acetyl chloride with catalytic aluminum chloride, Friedel-Crafts. Now here's one back from chapter 8 again. This one you had some time ago, and this is the Markovnikov hydration. Okay. Now here we have a triple bond, triply bonded carbon. Right, and so what we're going to do is hydrate that. Now since this is Markovnikov, okay, and we know it's Markovnikov because I see the mercury catalyst here. We have very, very low, this is mercury 2. Okay, the pH here is very low. And the way you would do this one, this is a mnemonic, okay, simply to draw a structure of a water molecule immediately above the triple bond, okay? And this is not a mechanism, this is just a mnemonic. And place that OH, okay, on this carbon, and place that H on that carbon. Okay, those two curved arrows again show you how this mnemonic would work. And if you follow that, and I'm going to use the letters pH for the benzene ring here. Remember, pH stands for phenyl. If you follow that line of reasoning, what do you end up with? You end up with something that we've come to know as an enol. Alright? This is our enol. Write that word in. This is enol. Now, most enols, what do? They undergo tautomerization. They tautomerize to what? They tautomerize to the keto form, which is the dominant tautomer. This is the keto form of that particular intermediate. So if you have to do this reaction, guys, this is your answer. Okay? This is how you get to the answer, but this is your answer. So in effect, if you have a terminal alkyne, right, a terminal alkyne, and you hydrate it, okay, you end up with what? A methyl ketone. Each and every time you do it. Okay, so this is another way to make a ketone. Alright, a little bit further and we'll take a break. Another approach is using diorganocopper reagents, okay? Sometimes these are called Gilman reagents. Gilman, and that's diorganocopper reagent, okay? And sometimes they even have other names associated with them, so on and so forth. Whatever the case is, you see copper here and you see two organic groups, okay? Now, the reaction that we're looking at here specifically is that of an acid chloride. Okay, a Gilman reagent can essentially replace any carbon halogen bond. All right, but here we're looking at acid chloride. Now, rather than get into a drawn-out detail of how this works, let me just give you a sort of a generic representation, okay, of how it works. Otherwise, it just gets a little bit complicated. Now, the reason these are called diorgano is because you have two of the identical organol groups. In this case, the simplest one, this is methyl. And we have an ionic bond here with lithium. Okay? And these sometimes are called cuprates. And the cuprates actually are clusters. They don't exist in singular form like this. And furthermore, what happens, the oxygen actually coordinates to the copper, the oxygen-copper coordination complex. And when all that occurs, this ensemble will deliver, okay, just one of these, okay, R groups, just one of them, not both. It makes a tetrahedral intermediate, but eventually the chloride breaks out, okay? So what I'm showing you here, this is not a mechanism. This is not a mechanism that we're looking at here. I'm just showing you the overall effect. So what happened? What happened was we formerly had a chlorine, but acid chloride has been replaced by that methyl group. So this is your organic product. Over here, these are your byproducts. Now the byproducts turn out to be pretty important, particularly that one because it still has a methyl group. It has our metal. This one's actually can be okay, less important, but this can actually be recycled. So again, this is one way to make a ketone, all right, out of a acid chloride. Let's just do one more, then we'll we'll have a little break. I'm flipping over to page 124 of your lecture notes. Let's try that one. It says predict the formula of the diorganocopper reagent needed to complete the following reaction. Okay. Well, first off, what do we have here? This is called benzoyl chloride. You remember this is called a benzoyl group, so this would be benzoyl chloride. Let me go ahead and write it out. Benzoyl, one word, chloride. All right, benzoyl chloride. And over here, you end up with your ketone. Okay? And notice too, we're using ethereal solvents. So really, what do you need? You need a source of ethyl groups. Okay? You're going to replace that chlorine with an ethyl group. But we want to keep this balanced. So what's a good way to do it? A good way to do it is to use an diorganic copper reagent. Okay? That we come to know as the Gilman reagent, or I even said the word cuprate earlier. Now you can write this out condensed, but if you want to draw it out showing a little more details, remember this always has a copper lithium bond, and that bond's pretty close to being ionic. But bear in mind, folks, that the R groups are going to be identical. Okay, you would not want a mixture of R groups here because that would give you a mixture of products. So I'm just going to go ahead and place those ethyl groups on there like that. Now, if you're a big fan of writing things out condensed, okay, you could do that as well. All right, you could do this just as well. Right? In other words, indicate that you have two ethyl groups, copper lithium. And the name of this compound, by the way, would be diethyl copper lithium. Okay. So folks, this is a good place to stop. We're going to continue with the reactions of carbonyl groups here in a little bit. See you a little later.